Hi, this is homework 5, part B. Here we will be taking a proportional controller and a third order transfer function in which we have 2 over 12s plus 1 cubed. We will be creating a Bode plot and we will be finding the value of the maximum stable controller gain, where the controller gain yields an amplitude ratio of 1 at a phase lag of 180 degrees. We will then simulate this closed loop response and then move into determining the ultimate gain, which is an ultimate period from our part B2. And we will then use Ziegler-Nichols method to determine the controller gain and reset time for a PI controller. And then finally, we will simulate the closed loop response of the PI controller in part B3 to a step change in set point. Right? So now we can go into our Google Colab. Here I have imported in our CHE template. So we can go ahead and start with defining our process transfer function, which is our GP, and that is going to be equal to 2 over 12s plus 1 cubed. So we have 2 over the quantity 12 times s plus 1, and this will be cubed. Okay, so next we need to define our GC, and this is going to be our process controller, and this is going to be the value that we are going to be fudging around with in order to determine what the maximum value is. So for now, I'm just going to keep this as 1, and I'm going to leave a note that this is our variable to change. And then next, I'm going to define a G, which we had done in part A, and it's basically in order to just simplify our process transfer feedback loop, so we can just write this as equal to GP times GC. So we go ahead and hit Shift Enter. Now that we have defined our process transfer functions, we can now go ahead and define what our x-axis is going to be for our Bode plot. So we can define that as our W's, referring to our omega values, and these are going to be equal to np.log space, since our Bode diagram is going to be in terms of, are going to have axes in which they are log values, and we will go from -2 to 0, and then we will support an index of 100. So next we want to define what our J omega is going to be equal to, and here we are going to use our simpy function, in which we will be calling simpy dot lambdify and calling for our omega term here, and be wanting to use the substitute function. So we will be substituting in our G term here, which is the G is equal to GP times GC. We will be substituting for W, and this will be times 1J. And as I stated in part A, we are calling J, and that is going to be equal to the square root of -1. However, Python is interpreting, or Google Colab is interpreting the J as the I term, so that is why we are using J here. And then we will be evaluating this with our substitution, in which we are substituting WS. Enter. All right, so next we want to create an array of our imaginary and real numbers, and this is going to be equal to np.imag for our imaginary number, and this is going to be evaluated at g, j, omega. And then for our real values, we are going to have np.real, and we are again going to be using g, j, omega. Okay, So next we want to define our m, which here is our magnitude ratio, and our m here is going to be equal to np dot square root of I squared plus r squared. So we can go ahead and just hit tab. So what we were taking here is the square root of our imaginary number squared plus our real number squared. So now that we have defined our magnitude ratio, we now want to define what our phi value is going to be. And our phi is going to be equal to our phase angle in degrees. And this is going to be equal to np dot arc, or here we're going to use a and 2. So we can put in 2 arguments, and we are again going to call our imaginary and then real. And this will give it to us in radians. However, we need to transfer it into degrees. So we will then want to multiply the arctan of our imaginary over real by 180 divided by np dot pi. So that is going to give us our angle in degrees. However, we need to use our np dot unwrap function, and this unwrap function is going to be translating our value of our arctan into feasible numbers. If we did not unwrap it, we would be getting invalid numbers for this simulation, so we just need to make sure that we're doing that. So now that we have this, we can hit Shift Enter. Oh no. Looks like I forgot a parenthesis. Get rid of that one. Shift Enter. Alright, so now that we have that in, we now want to go ahead and plot our Bode plot. So we can go fig is equal to make underscore subplots. And here we want our rows to be equal to 2, and our column is to be equal to 1, and 2. Our column is equal to 1, and we want this to be 2 plots stacked on top of each other, showing what a Bode plot. We want it to basically represent this plot right here, in which we have our magnitude on top and then our phase angle in degrees below. And it's easier to utilize these plots when they're stacked on top of each other. So going back to our Colab, we can go fig dot add underscore scatter. Here our x is going to be equal to our omega values. Our y is going to be equal to m, magnitude ratio, and our name here is going to be magnitude. And then next we're going to repeat this for our phi value. So I'm going to go ahead and just tab that in. I need to go ahead and modify where these plots will end up. So I'm going to call this row is equal to 1, column is equal to 1, and then for our phase angle, our row here is going to be equal to 2, column is going to be equal to 1. Shift Enter. Shift Enter. So here are our plots. However, you notice that our x-axes and our y-axes are incorrect here. They're very spread out, so we're going to need to go ahead and update our axes here. So we can go ahead and clear that output. Okay, so then we can go fig.update, and first we can go call our x-axes, and our type is going to be equal to log to have a decimal tick of 1. This is going to be for our magnitude plot. So row 1, column 1. And then next we want to update our y-axis for our magnitude plot. So again, here our type is going to be equal to log, row equal to 1, column equal to 1. All right, so now we want to go fig dot update our x-axis, and this is going to be for our phase angle. Type is again going to be equal to our log scale, and this is going to be equal to row 2 and then column 1. And then our last axis that we need to update is going to be our y-axis for the phase angle. Here we want our increments on our y-axis to have 180 so that we are able to visually tell where our maximum controller gain is going to be, and we're going to use that value in order to transfer to our magnitude plot in order to determine what our maximum value for our controller is going to be. So our row is again going to be equal to 2 and then column equal to 1. So now that we have updated all of our axes, we can go ahead and update the layout of our plots. So we can go ahead and make our height equal to 600, width equal to 600, and we can go ahead and give this plot the name. Text is equal to Bode plot. So let's hit Shift Enter and see what we get. So here is our Bode plot. At the top here we have our magnitude plot and below our phase plot. So I had wanted to print our 180 so that I can easily come across the x-axis here and then check what value our plot crosses 180. So it's around 0.14. So here's where we want to go to our magnitude plot and find the 0.14. So right now that is around 0.26, 0.23. Okay, so now we realize that at 180 degrees and then transferring up to here, we have not yet reached 1 for our magnitude. So we need to go back up and adjust our GC. So we can go ahead and try 2. Shift Enter all the way through. So again, at 180 we were around 0.14, and going to 0.14 we have reached 0.5. So we had basically doubled from our first iteration. So now we want to go ahead and try doubling this again to see if we can reach 1. We go ahead and run that. Again at 0.14 when we cross 180. And then going to 0.148, you can see that we are at 0.94. And then going to 0.1417, we have reached 1.04. So somewhere in that range, we are actually reaching our desired value of 1 for our magnitude ratio. So therefore, we can go ahead and clarify, or we can go ahead and determine that our maximum stable controller gain in which the amplitude ratio is 1 at a phase lag of 180 degrees, is going to be the value of 4. So we can just write that 4 is the optimal value for the controller. Okay. All right, so now that we have done that, we now want to go ahead and simulate this closed loop response. So going below our Bode plot, we can go ahead and call for our GCL, which is our closed loop function. And from our previous part in our previous homeworks, we know that this is going to be equal to GC times GP, and then all divided by 1 plus everything in the forward direction, which is GC times GP. For our simulation, we're going to call our T for our X, and then our Y for our Y, and we are going to want to run our simulate function, and we are going to want to simulate this closed loop function. And for our U here, we're going to call for our lambda, which is our anonymous function. We're going to go lambda T, this is going to be 1. And then for our N number, we're going to go ahead and go with 1,000. And for our time steps, we can just rock with 1 for now. So now that we have our simulation coded in, we now want to go ahead and plot this so that we can visually have a look and see what our process is going to end up over time. So doing so, we can say that fig2 is equal to make subplots, and then fig2 dot add underscore scatter, x is equal to t, y is equal to y, and we can go ahead and give this a name for our GCL, which is our closed loop, and then we can update our layout, fig2 dot update underscore layout. We can say that our height will be equal to 500, width here make 800, shift enter. So here you can see this is going to be our closed loop function simulating with our x-axis reaching 1,000, and this is with the controller gain of 4, and you can tell that this is indeed our point of stability with our oscillations neither growing nor fading away. And just to prove this, we can go ahead and increase this GC to 5 to see how this new plot will end up. And you can see that over time, our oscillations are steadily increasing. And then I'm going to do this one more time just for the value 1 below 3. And you can see that we are in fact reaching our steady state. So I'm going to go ahead and put this back at 4. And we have our steady oscillations. So that is part B2. Now we will move into part B3, in which we will determine the ultimate gain in the ultimate period from part B2 using the Ziegler-Nichols method to determine the controller gain and the reset time for a PI controller. All right, so let's go ahead and type in Ziegler-Nichols method. For our Ziegler-Nichols method, we want to go ahead and go to our Wikipedia page here. And for this homework, we are using a PI controller. So in this table here, we will want to use these values, and we are going to want to try to figure out what our ultimate gain is, KU, in which the point of the control loop has stable and consistent oscillations. So I'm going to go ahead and move some of these numbers in and then return back into Colab. So welcome back. I've gone ahead and brought in some terms from the Wikipedia page. So the KU is our ultimate gain, which is our GC from the previous part. So I'm going to go ahead and type in 4 there. The PU is the distance between peaks from our simulation plot, which is right here. So we're going from 112 to 69. We can just type in 112 to 69. Our KC, our controller gain, is going to be 0.45 of our ultimate gain. And then our reset time, tau I, is going to be 0.83 times our distance between the peaks. And then for our GC, we are taking the Laplace integral, and that is 1 over S for our GC. And then I've gone ahead and typed in our closed loop process transfer function for this second simulation, and it is again GC times GP over 1 plus GC times GP. So we can go ahead and shift enter. Now that we have ran that cell, we now want to go ahead and pull our simulation. You can go ahead and Control C, come back down here, Control V, that pasted in. So we'll need to change our closed loop function here to GCL2. Keep everything else the same. 2. And so let's go ahead and run this. Okay. So something's wrong here. Oh, so for my GC, I accidentally had divided. That should be multiplied by 1 plus 1 over tau S. So let's go ahead and shift enter and update that. All right, so here is our desired plot. So this is the plot in which we are at an ultimate gain of 4, which is our maximum gain from our previous part, in which we had derived from the Bode plot. And running the simulation there, we got these pretty big oscillations. However, using the proportional integral controller, using the Ziegler-Nichols methods with these constants and parameters, you are able to visually see that even though we are at the maximum controller gain, we are still reaching a steady state fairly quick instead of these rapid oscillations. So I believe I have just completed homework 5 part B. Thank you.